All right, testing my mic here. All right, my mic works. Let me just mute my secondary monitor. Just adjust this, and yep, that should be all right. Okay, so here we are yet again. Today is day 3, and there's another special thing about today. I finally started streaming on YouTube alongside Twitch. So I'm gonna learn as much as I can today, and yeah, let's see the progress that I make today. How do I set this? Yeah, there you go. Let me just set the camera. Is this good? Is it's hard to set the camera, isn't it? No, let's that should be it. Okay, perfect. So let's start. Or in fact, let's wait a second. Yeah, that should be good enough. So let me just open up everything here. Great. So yesterday we left at running our model from the normal Pytorch course that we are following. And at the end of the video, the tutor Daniel Bock challenged us to go out and learn more about the two algorithms used there. One is gradient descent, and the other one was back something. We'll check out the name. So that's what we're gonna begin with. We're gonna check out what gradient descent is and what the other algorithm is. So let's do that. Start on full screen. We covered a bit of this. I think we went to the multivariable calculus part. And as a reminder, he's doing this to get the local minima of the function. Yeah. Or rather, yeah, because it's impossible, not impossible, but it's hard to get the global minima. So, but it's easy to get the local minima because you can move left and right depending on what the output value turns out to be. Oh wait, let's just see. Back propagation, that's the word I was looking for. Wait, go back again. Yeah, it points more to 3. Hmm. Oh, so gradient descent is more like a concept, and back propagation is an algorithm which uses gradient descent. Okay, that's more like it, I think. Yeah. Go ahead again. Right, because if it's bumpy, then we'll get trapped in a ditch. Yeah, yeah, that makes sense. Should increase somewhat. Should increase a little. Okay. Should decrease a lot. Okay. Huh. The more negative it is, the more it will decrease. More positive it is, more it will increase. Right. Hmm. That isn't bad. I thought, I mean, 96% is really good, right? Maybe it isn't in the realm of machine learning. Wait, what? Hmm. I mean, I was gonna say, isn't that a six? So, yeah, I guess he's right. Of course, I mean, that's what I feel so, curious about machine learning. That is, with other realms of computer science, like not computer science, with other realms of software engineering, like whether it be game development or whether it be full stack development or making scripts or automations in general, you always like if someone tells you, or I can speak for myself, like if someone tells me to how, like can you make this website or can you make this automation script, immediately in my mind the code just starts forming up. But with if someone tells me, hey, can you write or can you make something which will differentiate between a dog and a cat, our famous hello world example on image classification, um, I wouldn't have been able to do so if you had asked this to me a couple of years before. Like even like it always fascinates me how machine learning does this. Not that I know more and more about it, my curiosity just increases. I want to learn more and more. Mm. All right. Three blue, one brown. Seems to be a math guy. His videos are really cool though. Okay, what I'm gonna take away from that is, as I've already known and mentioned in previous video, I think machine learning is, or at least the only area that I've come across which uses math, or the understanding that if you have a very good understanding of the math involved, you'll do way better. It's one of those fields like for web development and everything, you don't really need to use math there. Full stack development, automation, writing just silly scripts, but you do need to use that for machine learning and AI, which I am really passionate about because I'm a person who likes math like quite a lot of people out there. Anyhow, so that was good. Let's look at the algorithm then. Back propagation. Cost of this. Oh, he means a loss function by. Okay, a cost function, loss function. Same thing, different names. Yeah, because if this is really high, let's say this is 1, then this will become 0. So the lower the sum of all of this is, the better we are doing. Because if this is low, like this is supposed to be the real answer, but the neural network gives a low answer, let's say 0.01, or let's just do 0.02, right? Then what would happen? This would become very high, and since we are squaring a higher number, since we are not subtracting anything from this, the overall output of this squaring function thing is going to be higher. That makes a lot of sense.
Right now is that because thinking of the gradient vector as a direction in 13,000
did not turn on desktop
dimensions
audio
is, to
till
put it lightly,
now,
beyond the scope of our
sorry if you guys were watching without the audio and wondering what the hell was going on here.
imaginations. There's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So
Wait, what?
the magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments.
I think, we should change our strategy here. We should go back to the Pytorch course, and then once that's all done, we'll explore a bit of math with all the algorithms and everything that we have already done in the Pytorch course. So I think that's what we should do. So let's go back to Pytorch. Hopefully this thing comes up. There we go.
Still looking for the best smartphone under 15K? Check out the Infinix Note 40X 5G.
I'm coming from the bottom, but I'm rising to the top. Had to hustle every day, I ain't never gonna stop. From the shadows to the spotlight, I'm shining like a star.
Infinix Note 40X 5G. Sale is live. Only on Flipkart.
This comprehensive course will teach you the foundations of machine learning and deep learning using Pytorch. Pytorch is a machine learning framework written in Python. You'll learn machine learning by writing Pytorch code. So when in doubt, run the provided code and experiment. Your teacher for this course is Daniel Bork. Daniel is a machine learning engineer and popular course creator. So enjoy the course and don't watch the whole thing in one sitting.
Welcome back. In the last video, we set up a loss function and we set up an optimizer and we discussed the roles of each. So the loss function measures how wrong our model is. The optimizer talks to the loss function and goes, well, if I change these parameters a certain way, does that reduce the loss function at all? And if it does, yes, let's keep adjusting them in that direction. If it doesn't, let's adjust them. Welcome back. Whew, we're in an exciting streak of videos coming up here. I mean, the whole course is fun, trust me, but this is really exciting because training your first machine learning model seems a little bit like... Welcome back. In the last video, we set up a loss function and we set up an optimizer and we discussed the roles of each. So loss function measures...
Now it makes sense. Like SGD would be our optimizer, right? And loss function would be our cost function, as mentioned in the other video by blue one, brown one. I forgot the channel name. Excuse me for that. Anyhow, yes, that makes sense. So if the loss is too much, then the optimizer comes in and then tries to readjust this. Now this is a linear function, so it's going to be easy, right? But when you have a multivariable function, right, it's gonna become hard.
This is how wrong our model is. The optimizer talks to the loss function.
A model would do cubic or a... But is there a specific name to a function with x raised to 4? Anyhow, you get the point. With higher exponents, how will it will become really hard, right?
And goes, well, if I change these parameters a certain way, does that reduce the loss function at all? And if it does, yes, let's keep adjusting them in that direction. If it doesn't, let's adjust them in the opposite direction. And I just want to show you, I added a little bit of text here just to concretely put down what we were discussing. Inside the optimizer, you'll often have to set two parameters, params and LR, where params is the model parameters you'd like to optimize. For example, in our case, params equals our model 0 parameters, which were, of course, a weight and a bias, and the learning rate, which is LR in optimizer. LR stands for learning rate, and the learning rate is a hyperparameter. Remember, a hyperparameter is a value that we, the data scientist or machine learning engineer, sets, whereas a parameter is what the model sets itself. defines how big or small the optimizer changes the model parameters. So a small learning rate, so the smaller this value, results in small changes. A large learning rate results in large changes. So another question might be, right? So the smaller this value model sets itself, defines how big or small the optimizer changes the model parameters. So a small learning rate, so the smaller this value, results in small changes. A large learning rate results in large changes. So another question might be, well, very valid question, hey, I put this here already, is which loss function and which optimizer should I use? So this is another tough one because it's problem specific, but with experience in machine learning, I'm showing you one example here. You'll get an idea of what works for your particular problem. For a regression problem like ours, a loss function of L1 loss, which is MAE in Pytorch, and an optimizer like torch.optim/SGD, like stochastic gradient descent, will suffice. But for a classification problem, we're going to see this later on, not this one specifically, where there are photos of a cat of a dog, that's just an example. Of a binary classification problem, you might want to use a binary classification loss. But with that being said, we now are moving on to, well, here's our whole goal, is to reduce the MAE of our model. Let's get the workflow. We've done these two steps. Now we want to build a training loop. So let's get back into here. There's going to be a fair few steps going on. We've already covered a few, but hey, nothing we can't handle together. So building a training loop in Pytorch. So I thought about just talking about what's going on in a training loop, but we can talk about the steps after we've coded them. How about we do that? So we want to build a training loop and a testing loop. How about we do that? So a couple of things we need in a training loop. So there's going to be a fair few steps here if you've never written a training loop before, but that is completely fine because you'll find that the first couple of times that you write this, you'll be like, oh my gosh, there's too much going on here. But then when you have practice, you go, okay, I see what's going on here, and then eventually you'll write them with your eyes closed. I've got a fun song for you to help you out remembering things. It's called the Unofficial Pytorch Optimization Loop Song. We'll see that later on, or actually I'll probably leave that as an extension, but you'll see that you can also functionize these things, which we will do later in the course so that you can just write them once and then forget about them. But we're going to write it all from scratch to begin with so we know what's happening. So we want to, or actually step 0 is loop through the data. So we want to look at the data multiple times because our model is going to, at first, start with random predictions on the data, make some predictions, we're trying to improve those, we're trying to minimize the loss. To make those predictions, we do a forward pass. So forward pass, why is it called a forward pass? So this involves data moving through our model's forward functions. Now I say functions because there might be plural, there might be more than one. And the forward method, recall, we wrote in our model up here. Forward. A forward pass is our data going through this function here. And if you want to look at it visually, let's look up a neural network graphic. Images, a forward pass is just data moving from the input to the output layer. So starting here, input layer, moving through the model. So that's a forward pass. Also called forward propagation. Another time where more than one name is used for the same thing. So we'll go back down here, forward pass, and I'll just write here, also called forward propagation. Propagation. Wonderful. And then we need to calculate the loss. So forward pass, let me write this. To calculate or to make predictions on data. So calculate the loss, compare forward pass predictions. Oh, there's some thunder going in the background here of my place. We might be in for a storm. Perfect time to write code. Compare forward pass predictions to ground truth labels. We're going to see all this in code in a second. Calculate the loss, and then we're going to go optimize the zero grad. We haven't spoken about what this is, but that's okay. We're going to see that in a second. We're not going to put too much there. Loss backward. We haven't discussed this one either. There's probably 3 steps that we haven't really discussed. We discussed the idea behind them, but not too much in depth. Optimizer step. So this one is loss backwards is move backwards. If the forward pass is forwards, like through the network. The forward pass is data goes in to out. The backward pass data goes, or calculations happen backwards. So we'll see what that is in a second. Where were we? Over here. We've got too much going on. I'm getting rid of these. Moves backwards through the network to calculate the gradients. The gradients of each of the parameters of our model with respect to the loss. Oh my gosh, that is an absolute mouthful.
That's an absolute mouthful, I agree, but I think I get a feeling of what's happening. So it goes all the way to the front, right? Then it uses the one black two, that channel's that squaring thingy, right? To see what it calculates the loss basically, right? And then based on the gradients, like as it moves backwards, it knows, hey, if I have to optimize it, I need to go this direction rather than the other direction. And then it optimizes it using whatever algorithm we've set to be the optimizer. Now, yeah, I know that might not make sense at the beginning. Even I am a bit confused and all. But I think it makes a bit of sense to me.
Probably for now. Yeah. Optimizer step. This is going to use the optimizer to adjust our model's parameters to try and improve the loss. So, remember how I said in a previous video that I'd love you to watch the 2 videos I linked above, one on gradient descent and one on backpropagation? If you did, you might have seen like there's a fair bit of math going on in there. Well, that's essentially how our model goes from random parameters to better parameters, using math. Yeah. Many people, one of the main things I get asked from machine learning is how do I learn machine learning if I didn't do math? Well, the beautiful thing about Pytorch is that it implements a lot of the math of backpropagation. So this is backpropagation. I'm going to write this down here. This is an algorithm called backpropagation, hence the loss backward. We're going to see this in code in a second, don't you worry. And this is gradient descent. So these 2 algorithms drive the majority of our learning. So backpropagation, calculate the gradients of the parameters of our model with respect to the loss function, and optimizer step will trigger code to run gradient descent, which is to minimize the gradients. Because what is a gradient? Let's look this up. What is a gradient? I know we haven't written code yet, but we're going to do that. Right. Images. Gradient, there we go. Change in Y, change in X. Gradient is from high school math. Gradient is a slope. So if you were on a hill, let's find a picture of a hill. Picture of a hill. There we go. This is a great big hill. So if you're on the top of this hill and you wanted to get to the bottom, how would you get to the bottom? Well, of course, you just walk down the hill, but if you're a machine learning model, what are you trying to do? Let's imagine your loss is the height of this hill, and you start off with your loss is really high. and you want to take your loss down to 0, which is the bottom, right? Well, if you measure the gradient of the hill, the bottom of the hill is in the opposite direction to where the gradient is steep. Does that make sense? So the gradient here is an incline. We want our model to move towards the gradient being nothing, which is down here. And you could argue, yeah, the gradient's probably nothing at the top here, but let's just for argument's sake say that we want to get to the bottom of the hill. So we're measuring the gradient, and one of the ways an optimization algorithm works is it moves our model parameters so that the gradient equals 0. And then if the gradient of the loss equals 0, well, the loss equals 0 too. So now let's write some code. So we're going to set up a parameter called, or a variable called epochs, and we're going to start with 1. Even though this could be any value, let me define these as we go. So we're going to write code to do all of this. So epochs. An epoch is one loop through the data. Dot, dot, dot. So epochs, we're going to start with 1. So one time through all of the data. We don't have much data. And so for epoch, so let's go this. This is step 0. 0. Loop through the data. By the way, when I say loop through the data, I want you to do all of these steps within the loop. And do, dot, 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 loop through the data. So for epoch in range epochs. Even though it's only going to be 1, we can adjust this later. And because epochs, we've set this ourselves, this is a hyperparameter because we've set it ourselves. And I know you could argue that, hey, our machine learning parameters of model 0, or our model parameters, model 0 aren't actually parameters because we've set them, but in the models that you build in the future, they will likely be set automatically rather than you setting them explicitly like we've done when we created model 0. Oh my gosh, this is taking quite a while to run, that's all right. We don't need it to run fast, we need to write some more code in. Come on. There's a step here I haven't discussed either. Set the model to training mode. So Pytorch models have a couple of different modes. The default is training mode. So we can set it to training mode by going like this. Train. So what does train mode do in a Pytorch model? My goodness, is there a reason my internet is going this slow? That's all right, I'm just going to discuss this with talking. Again, list. Train mode. Train mode in Pytorch sets, oh, there we go, requires grad equals true. Now I wonder if we do with torch.nograd, remember nograd is similar to inference mode, will this adjust? See, I just want you to take note of requires grad equals true. Actually, what I might do is we do this in a different cell. Watch this. This is just going to be, rather than me just spit words at you, I reckon we might be able to get it working doing this. Oh, that didn't list the model parameters. Why did that not come out? Model 0.eval. So there's two modes, eval mode and train mode. Model.eval parameters. Okay, we're experimenting together on the fly here, and actually this is what I want you to do, is I want you to experiment with different things. It's not going to say requires grad equals false. With torch.nograd. Model 0.parameters. I don't know if this will work, but it definitely works behind the scenes. And what I mean by works behind the scenes and not here, it works behind the scenes when calculations are being made, but not if we're trying to explicitly print things out. Well, that's an experiment that I thought was going to work and it didn't work. So train mode in Pytorch sets all parameters that require gradients to require gradients. So do you remember with the picture of the hill, I spoke about how we're trying to minimize the gradient? So the gradient is the steepness of the hill. If the height of the hill is a loss function and we want to take that down to 0, we want to take the gradient down to 0. So same thing with the gradients of our model parameters, which are here, with respect to the loss function, we want to try and minimize that gradient. So that's gradient descent, is take that gradient down to 0. So model.train, and then there's also model 0.eval, so turns off gradient tracking. So we're going to see that later on. But for now, I feel like this video is getting far too long. Let's finish the training loop in the next video. I'll see you there. Friends, welcome back. In the last video, I promised a lot of code, but we didn't get there. We discussed some important steps. I forgot how much behind the scenes there is to a Pytorch training loop. And I think it's important to spend the time that we did discussing what's going on, because there's a fair few steps, but once you know what's going on, I mean, later on we don't have to write all the code that we're going to write in this video. You can functionize it. We're going to see that later on in the course, and it's going to run behind the scenes for us. But we're spending a fair bit of time here because this is literally the crux of how our model learns. So let's get into it. So now we're going to implement the forward pass, which involves our model's forward function, which we defined up here when we built our model. The forward pass runs through this code here. So let's just write that. So in our case, because we're training, I'm just going to write here. This is training. We're going to see .eval later on. We'll talk about that when it comes. Let's do the forward pass. So the forward pass, we want to pass data through our model's forward method. We can do this quite simply by going ypred, so y predictions, because remember, we're trying to use, our ideal model is using x test to predict y test on our test data set. We make predictions on our test data set. We learn on our training data set. So we're passing, just going to get rid of that because we don't need that. So we're passing our model xtrain, and model 0 is going to be our current model. There we go. So we learn patterns on the training data to evaluate our model on the test data. Number 2, where are we at? So we have to calculate the loss. Now, in a previous video, we set up a loss function. So this is going to help us calculate the what. What kind of loss are we using? We want to calculate the MAE. So the difference or the distance between our red dot and a green dot. And the formula would be the same if we had 10,000 red dots and 10,000 green dots. We're calculating how far they are apart, and then we're taking the mean of that value. So let's go back here. So calculate the loss. And in our case, we're going to set loss equal to our loss function, which is L1 loss.
Comments too, so that we understand what would be going on later if we were to check this later. That is. So we begin our training here and we are looping through the data. We are setting the model to training mode, and training mode sets the gradients to wherever gradients is needed, but the eval mode doesn't. Then we are doing forward pass, or in other words moving forward, like predicting, basically predicting what the value would be for our function. And now once we got our predictions, we are calculating the loss through mean absolute difference in this case, or as Pytorch calls it, L1 loss. Same name, different sorry, it should be different name, same things. Yeah, okay. Anyway, model 0.eval. I wonder why we're turning off the gradient tracking in the end though.
In PyTorch, but it is MAE, YPred, and YTrain. So we're calculating the difference between our model's predictions on the training dataset and the ideal training values. And if you want to go into torch.nn loss functions, that's going to show you the order, because sometimes this confuses me too, what order the values go in here, but it goes prediction first, then labels. And I may be wrong there, because I get confused here, my dyslexia kicks in, but I'm pretty sure it's predictions first, then actual labels. Do we have an example of where it's used? Yeah, input first.